All right, Physics H. I want to talk a little bit about these energy bar diagrams. So, in the simulation software, we saw these bar diagrams being generated by the software. Now, we need to talk a little bit about, how we would generate these bars ourselves when these different energies exist. So, PEG is gravitational potential energy. Okay, so I should probably have a little bit of scrap paper here to show that, but of course I don't have anything right here. So PEG is what we call gravitational potential energy, gravitational PE. And an object possesses, or there is gravitational potential energy in a system when there's an object in that system that's elevated off the ground and it has some place to move down, right? Tape dispenser sitting on the desk, right, doesn't really have any gravitational potential energy because where is it going to go? Now, if I move it towards the edge of the desk and I say, okay, I'm going to have an opportunity to drop this, then yeah, I would say, okay, it has gravitational potential energy relative to the ground. So an object, has potential energy when it has somewhere to go. All right? So that's going to be related to the first one here. And that gravitational potential energy is directly proportional to the height the object is off the ground. PES is what we call spring or elastic potential energy. All right? This is when you have literally a spring, this pen here, right? I literally have a spring compressed, right? And it stores energy. I let that spring go, it's going to go flying off my pen here. I don't want to lose it because I have to put this pen back together to be able to, so I compress the spring, let it go. It went flying. All right, it went flying. Probably couldn't even see it in the video. I didn't see it with my naked eye. So anyhow, when a spring is in a system and it is compressed, then we say there is spring or elastic potential energy in the system. It can be compressed or stretched, right? Like a rubber band, if you stretch it, it stores elastic potential energy or spring potential energy. And that's proportional to what we say is X, which is how far the spring is stretched. All right. KE is kinetic energy. All right. And that's proportional to how fast the object is moving. It's actually proportional to how fast the object's moving squared. So I'll give you the equations for these different energies a little bit later on. Mass is also factored into PEG and KE, and something called spring constant is factored into spring potential energy. The last one here, E other. Well, sometimes you need to use that. You need to use that when some sort of energy must be coming into the system that isn't one of these three, right? If it's nuclear, heat, thermal, if it's energy from a person, which we call work, if it's, solar energy or something, electrical energy, we might have to use that E other, fuel energy. Now over on this side, so these bar graphs are the energy, the initial energy state. Where's the energy distributed initially? This is the final state, or the later state, so initial and final here. E internal is thermal energy, right? It's thermal energy, or internal energy. In the simulation, they called this thermal, I think. You'll remember from the simulation, you never start off with thermal energy, right? You never start off with thermal energy initially. It doesn't exist until you turn on friction, or if something drops and hits the ground and makes a big noise, right? And then the thermal energy builds up. If I drop a bouncy ball on the ground, it's gonna go. Actually, I think there's a drawing of one in here somewhere. It's gonna bounce, right? Bouncy ball. It's gonna go boink, 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 boink until it just rolls and stops, right? So it's gonna bounce and bounce and bounce and bounce and then stop. Well, what happens there is all that initial gravitational energy I had in the ball initially, right, got converted into kinetic energy on the way down. got converted back to potential energy here, but what happened, right? I lost a bunch of energy here. It didn't bounce as high. When it hit the ground and it compressed, it made noise, right? It sent vibrations through the ground, it made noise. It got converted into internal or thermal energy, believe it or not, or sound energy, light energy. You know, energy escaped the system. The system is the ball and the ground here. So the energy eventually escapes the system and gets radiated outwards in the form of light, heat, and sound. Right? Pretty interesting to think about that. Right? So I'm going to take a stab at this, do this first one for you. All right? So an object starts from rest on a frictionless ramp and slides to the bottom. All right? So starts up off the ground, right? It has an initial height. It actually has a little final height too, maybe. You know, it gets lower. So initially, you know, if I think about where's the energy contained initially, well, there's a lot of gravitational potential energy. I'm going to make it 4 bars here. All right. Is there any spring energy? No, not initially. Is there any kinetic energy? No, not initially. Is there any E other? I'm not sure. I'm not sure if there's any E other. We don't use this column unless we have to, you know, unless we end up in a situation where I can't explain it. At the bottom, though, I've gotten rid of most of my gravitational energy, right? Maybe I've gone from 4 units off the ground to only 1. Maybe it's got a little bit farther it could go down. So I've dissipated most of my gravitational energy at the bottom. Now, where did it go? I would say it has a lot of kinetic energy at the bottom there, right? Let's say this one's frictionless. All right, let's say this one's frictionless, right? So that means I'm not going to have any thermal energy built up. All right, let's say it's frictionless. Well, there's no spring. I've already declared only 1 unit of PEG. There's no thermal, so that must mean I converted 3 of those units of energy into kinetic energy. Now this is where the currency of physics comes into play, right? The counting has to work out. All right, I have to have accounted for everything I had initially. So I had 4 units of energy here. I had 1, 2, 3, 4 units of energy here. All right, so that's pretty cool. Number 2 here, right? A block slid along a high friction surface. So we have high friction here with some initial speed and comes to rest after sliding a certain distance. Now the system here, I should have declared that up here. It's the block, the ramp, and the earth, you know, gravity. This one is block, the ground, and earth. The ground and earth, I guess those are the same thing, but they apply different forces, right? The ground's applying a normal force and a frictional force. The earth is overall total. The ground in this area, you know, the earth overall total is providing gravity, right? So when you declare the system based on what forces are interacting here, all right? So I have no gravitational energy here because there's no change in height happening. There's no change in gravitational energy, so I don't even say it has any. Spring energy, I have no spring. Kinetic energy, yep, I start off with a lot of initial kinetic energy. What the heck, I'm gonna make it 4 bars. Maybe that's a mistake. Sometimes you make these too big. It's best off to do these with pencils sometimes. All right, so then at the end, E other, I don't know. Do I need any E other? This would be like, remember, E other, this is like an outside energy source. Or an energy source that's not accounted for here. And notice there's no E internal ever in the initial graph, right? Because like I said, we never start with thermal energy. Thermal energy comes into play due to friction as the object moves. Now, I have nothing else to do here. Let me look at this one. PEG, no, still no PEG, still no spring. Kinetic energy? Nope, because it's not moving. So that leaves us only one option. All of that initial kinetic energy must have gone into internal energy. And in fact, that's what happens. The block gets warm. And literally, all that kinetic energy, the block moving, gets dissipated into the ground. It's kind of a fascinating thing. Into the ground, actually into itself as well, in the terms of vibrations of the material. And that energy that gets stored up in here, I think about it, all these molecules vibrating, right? if you go to that friction simulation, you can see this happening in that simulation. It's pretty neat. And then it actually gets radiated off as infrared radiation, heat, right? It gets radiated back out of the ground and the block back into space. It's kind of a neat little thing. All right, let me see if I can find one that has an E other required for us here. Here's what we go. A good one. I'll add one here. Create your own system, right? A car driving up a hill at a constant speed, right? Let's say the speed doesn't change. So initial, final. So it's car, ramp, and earth, right? So let's say it starts off at 0 height. Basically, always make our lowest point the 0 height, right? So I have no initial gravitational potential energy for this car. I have no spring. I do have KE initial. How much do I have? Do I make it 4 bars? I don't know. Let's go for it. 4 bars of kinetic energy. All right. So E other, I don't know yet. We'll see. As it goes up the ramp, right? Let's see what's happening here. Have we increased gravitational energy? Yes, we have. We've gone off the ground, right? We've gone some height here. So therefore, I've gained gravitational energy. How many bars? I don't know. Maybe 2? Maybe 2 bars of gravitational energy? But since I'm going at a constant speed, that means the kinetic energy has to remain constant. That means I still have 4 bars of kinetic energy, right? So where the heck did this come from? I don't have anything over here to account for it. Where did the gravitational energy come from? How did I get this car uphill? Well, you may realize that as you go up and down hills, you get terrible gas mileage, right? So you're using more energy. So I have to add, and you know what? In fact, I probably built up some internal energy, right? Maybe due to friction, air resistance. You know, I didn't say anything about it here. You can get specific. Maybe this is the air drag on the car, right? You think that would happen, right? Friction. So now, look, I have 1, 2, 3, 4, 5, 6, 7 bars of energy here. 7 units of energy in the final state. I only have 4 to start off with. That must mean there must be 3 units of other energy coming into the system somehow. And what that E other is fuel, right? Chemical potential energy, right? You burn fuel. My old inefficient SUV, I can get almost 20 miles per gallon cruising down the highway at 55 miles per hour on cruise control, right? Once I get up to speed, I can get almost 20 miles per gallon in that beast of a old inefficient SUV. More like 19 miles per gallon I've gotten with ethanol-free gas, 91 octane, fresh oil change. I'll get 19 miles per gallon on the thruway going at 65. I can even get a little bit better if it's like 55, a little bit better gas mileage, a little slower. But then when I commute back and forth from school, I get 11 miles per gallon. I get 11 miles per gallon commuting from my house to school. Nearly cut the gas mileage in half because that's a heavy vehicle. It's got a truck frame, heavy engine. It's not very aerodynamic. So when you go up those hills, up and down hills, because I have to come up Thompson Road every day or Sealy every day. I got to pick one of those hills to come up every day. So gas mileage goes way down. It's all stop and go. In fact, I have to go up James Street to get to my kids' school, then come down to Erie Boulevard, then go back up. Then go back down again and come up Kimber. Actually, now that I think about it. So I have all these hills on my commute, and my gas mileage gets cut in half. So that's the E other here. That's where you would use that. I'm going to stop this video here. I'd like you to try to do the rest. I didn't do one with a spring. Hopefully you can figure it out. We'll go over these in class. Next one, we'll learn the equations here. All right? Have a good one.